Good morning, everyone, and thank you for joining us. Today's webinar is a look at mercury in bottled water from around the world, presented by John McWatters, our product specialist. We will be taking questions throughout the presentation, so feel free to use the question function and submit the questions throughout, and we'll address those at the very end. I'm going to turn it over to John now.
Good morning, everybody. I'm John McWatters, Mercury Product Specialist with Teledyne Leeman Labs. Today I'm going to go over actually something that's was one of my very first experiences with 1631. In retrospect, it was actually fairly easy thing to cut my teeth on. Bottled water is generally very clean, and this was a very interesting project to start out with. So we're going to look at a little bit of 1631 in reference to bottled water, 1631 itself, and some of the other issues or some of the other bullet points underneath of this on this presentation are subjects for full presentations themselves. So, like I said, we're just going to hit some of this in relation how it pertains to this project, the bottled water from around the world. That being said, let's get started here, and some brief background about it. We'll go over a little bit of where the water was sourced. We'll hit, like I said, some of the method points in relation to this particular project. The amount of preparation that we went into, the experimental procedure, the handling, and all that sort of thing. And then at the end, we'll talk a little bit about how the water rated at the very end. So a little bit of background method here. Consumption of bottled water has really taken off in years. I'd really be curious to get back in and research some of what's been happening in the last 10 or 15 years. But water usage or bottled water purchasing and usage has been roughly 6 times higher between 76 and 99. There's 3 basic types of bottled water: mineral water, spring water, and plain old purified water, which is essentially the same thing that can come out of your tap. Natural mineral water is basically just water, sometimes spring water, sometimes deep wells. Often it has a lot of some artesian wells. There's a lot of minerals, certain minerals, depending on the ground that it comes out of. So there's natural springs and also tapped wells. Spring water is almost the same thing, except it doesn't always have the same mineral composition, background composition of the other minerals inside of it. Purified water is, like I said, just basically the same as what comes out of your tap. It's sourced from various locations, purified, cleaned up, and bottled for our drinking pleasure. We got some of our salespeople sent in to my boss bottled water from a pretty diverse, geographically diverse areas here that we can see here at the bottom. We didn't, for this particular project, we didn't delineate by the type of water that we were using in the project. We just lumped them all into the category of bottled water. You can see that we kind of hit lots of spots across the globe, and it was interesting to see the results at the end, which we'll get to pretty soon. Filtered and unfiltered water, we'll talk about the scope, and this is taken kind of just bullet points right out of the method as it pertains to this. So we'll go over a few of these things, and like I said, there is tons and tons of details under some of these things that can be an entire presentation on its own and get into it. Surface water and groundwater is what this procedure is. It's basic. That's the matrix. That's the type of sample that this is made for. Across those, there are various cleanlinesses and things of that nature. The surface water, groundwater that you would be drinking is generally pretty clean water. The saline waters can be a little bit more difficult because of all the other minerals and things that are dissolved into it. And of particular interest, not in this study, but in later studies, municipal wastewater has some special concerns since it does carry, it's loaded with a little bit more X factors, ABC minerals and such that can be interferences or false positives, false negatives. I'm not fully versed on all of the EPA's sources and reasonings, but it's been since the 70s that clean water has been become more and more important. I believe it was somewhere in the 90s when mercury was becoming more and more prevalent, and people in the general public were much more aware of it. This method deals with generally very low-level mercury, and it's becoming more and more popular for that reason as concerns with mercury are getting, everything is pushed to try to go lower and lower and lower, and the safety of the water is the amounts that they say is safe is being dropped lower and lower all the time. 1669 is actually an entire method of how to safely or how to cleanly gather and transport and maintain the sample's integrity on its way from the sample site to the lab, and some handling techniques about how to keep everything clean so that nothing gets contaminated, so that you don't have false positives. Keeping things clean is paramount, and not contaminating it with other mercury sources, since mercury at these levels is fairly prevalent in laboratories in the world, all over the world. There is a little bit of background mercury everywhere you go. There's a little bit here and there's a little bit there. The range for this particular method, the starter calibration, is 0.5 ppt to 100 ppt. So there's, if you find out that your samples, if you're doing samples of this nature, if you do find that all your samples are generally much lower, this can be reduced down. If you find that generally your samples are much higher, or that you have interferences that you would like to try to keep their effects, to try to lessen their effects, dilutions before you begin the digestion is highly recommended to get within a working range. But it all depends on what typically comes into the laboratory. The method detection limit, as stated in the method, and under scope and application, these are all the recommended line items for the method, is 0.2 ppt. The method is performance-based, meaning that you have a little bit of leeway in some of the things that you can do. There is terminology. If you read through, it's a fairly extensive method. There's a lot of musts and shoulds and suggestions and things that have to go exactly. If you do decide, or if you do find that you need to modify greater than is allowed for in the CFRs mentioned here, then you can, if you prove your work and that you have good quality control and that you are confident in your results, you can apply for an alternate test procedures dispensation from your regional EPA office. This method was started before, well, kind of on the cusp is what my understanding is. There are the old bubbler systems, and then there's also flow injection systems. And throughout the method, as you read through it, there's some of the calculations are inherently based on one or the other's methods. We'll be talking about the flow injection method because we use an automated system for doing this in this particular project. Getting the sample to the laboratory is very important. You want to have it in clean containers, sometimes glass, sometimes certain kinds of plastics are allowed. The plastics, they do need to be certain types of plastics, as mercury can go through or can be a contaminant on some plastics if they're not prepared and cleaned properly. There's different fractions of it depending on what you're trying to do with a particular sample. There's a dissolved portion, and then there's also the filtrated portion, and then some samples are just tested as a total sample regardless of whether you're getting the filtered portions. And then there's specific details about where you preserve it, if it's going to be the filtered or the unfiltered mercury sample. Preservation is listed here with using approximately 5 mils per liter to stop the biological or chemical reactivity to stop it so that the mercury is locked in its current state. That can also be done in this method with the bromine solution is also listed in the method using a certain amount of the potassium bromide solution also to preserve it and stop the biological or chemical activities. Once the samples have been digested, generally for a 12-hour period, then the BRCL is reduced with the hydroxylamine. This gets rid of the excess that is not used up during the digestion. It's very important that during the digestion period, whether it's 6 hours or 12 hours, 12 hours is the suggested time period for these particular samples. It should maintain its characteristic yellow color of the BRCL during that entire time. If it does not, then you know that the BRCL was used up breaking down the sample, and that more has to be added to that sample to assure that the mercury is being broken down out of the organic matter and is available for the next step, the reduction of the mercury. The mercury is reduced. Once it's liberated from the sample, it's reduced with stannous chloride, and then on our automated system, it will go through a gas liquid separator, and then that is applied to the first gold trap. Purging the sample, the old school method was to have a prescribed amount of sample in a vessel, the stannous chloride's added to it, it's sealed into a system, and the gas purging is simply the bubbling of the gas through the sample in presence of stannous chloride to liberate the mercury into the vapor phase so it can be captured by the gold trap. With our system, the liquid is mixed with stannous chloride in line. Then it goes over a gas liquid separator where it doesn't bubble, but it chemically reacts, and then on a very thin post, there's a lot of surface area and a lot of argon flowing around that for the mercury to go out of the liquid phase to evaporate basically, or vaporize into the argon stream and be carried to the gold trap. Mercury traditionally was captured on what they would call sample traps, gold traps. Gases or liquids would be bubbled sometimes on site and then brought back to the laboratory. That's the reason for the verbiage in the method for 2 gold traps. That's where the 2 gold trap system comes from. Sample traps would be used to capture the mercury onto the gold trap, and then back at the lab, the mercury from that trap was then transferred, heated in line in a sealed system. The vapor, the mercury comes off as a vapor, and then it would be captured on a second gold trap. The reason for this historically was because gold traps, depending on their shape, the amount of gold, the aggregate that the gold coating is on, they have different characteristic peak shapes when they come off, the shape of their peaks, and it's really hard for people or computers to evaluate those. So if they were several different ones, it makes it a lot harder to get very accurate results, to create a good calibration, get good numbers back. In the system that we use, we have the capability of doing 2 gold trap, but basically we just use the first gold trap to gather the mercury, and that also has the second benefit of a lot of other things that could be interference that are liberated with the mercury at the trap actually flow through past the gold, and then that allows for us to have just pure mercury vapor being shunted over to the detector when we've amalgamated, basically soaked up enough mercury onto the gold trap to get a very strong peak. That's the whole purpose of pre-concentrating on a gold trap. One is to get rid of some of the interferences that can cause interferences at the detector. The other is to increase it. We pull up more sample than a normal run would and basically concentrate it to get a larger detectable peak, and this gives us better results further and further down, closer and closer towards the to the 0 point. It's very important to have very clean argon, pure argon. Impurities in that can cause what we call quenching, and we won't talk about that too much because the gold trap does virtually eliminate that. But other species that are in the argon gas can, O2, N2, can actually suck up some of the, not to get too technical there, but can reabsorb some of the energy that the mercury is giving off when it's excited by the light source. The light source is giving off light at 253.7. That's the mercury wavelength. Some more definitions taken right out of the method 1631. Total mercury for all purposes is basically all the recoverable, or total mercury is basically synonymous. Dissolved mercury is all the forms that are found in the filtrate. Contamination and interference. This is, the contamination side is actually, like I said, a thing that you can go for hours and hours on. Prevention of contamination throughout the whole samples chain, from sampling to transport to handling in the lab to preparation in the lab. Labs are, like I said, there's a little bit of mercury everywhere, but in a lab, sometimes the person next to you can be using a technology or a chemistry that actually has excessive mercury in it, and those can be hot sources of cross-contamination. If you have to share particular scales or pipetters or any kind of preparation sort of thing, some of these things, knowing what is the sources and trying to prevent cross-contamination is paramount to making sure that we get good, accurate results, true results, real-world results. Like I said, we'll just go over a few of the bullet points here talking about it. Metals, staying away from metals, using plastic parts. Clean labs are expensive. Clean labs can actually have everything is some sort of plastic that's easy to clean, that doesn't corrode, that isn't a source of grabbing a little mercury and concentrating it and then letting it, a little flake of some kind of corrosion off into the environment. There's all kinds of substances in a lab, as I said, that that do have are possible contaminants to the work area handling. Secondary contact is a big deal in a laboratory when you're prepping samples and standards and handling everything in the laboratory. Be aware of not just, getting a little bit of something into something else, but handling it. It's just like, the way I think about it is mercury contamination is sort of like cold season in the wintertime. Door handles, anything that's a secondary source or secondary can be handled for one thing. How you set your caps down, all of these sorts of things, even the air, depending on a certain laboratory, what the ventilation is like, can be a source for contamination. Clean areas, it's best to have clean areas. Try to provide for particulate-free air. The system that we use when we actually get the samples digested and over to the system actually has an enclosure with HEPA-filtered air, and the air is evacuated through this enclosure to keep everything above the samples while they're sitting there kind of naked and open, that all the air that's in there is going to have no particulate. And particulate is generally where you will find, you don't generally, from what I've read, most of the time mercury that's in the air is associated on particulate. So one small particulate into a blank or a sample can actually be enough to give you a false positive. You want to try to stay away from metal. It's just a place where mercury does amalgamate with gold, silver, I believe platinum, and it will combine with some other things of that nature. So you do not want to have being a dirty, rusty hood. You want to try to be as pristine and clean as you possibly can with the facilities that you have. Some of the things that you do need to be kind of concerned with if your air quality is of question is when you're taking the lids off of reagents, bottles that you're preparing, samples that you're preparing, keep the lids on. Be very, very, very careful. A lot of this is kind of, just think of it, like I said, as there's a little bit of mercury everywhere. Just some of these things are common sense if you think along those lines. Don't take a lid off of a sample while you're preparing or adding sample or reagents. Take the lid off just for enough time to get the reagent into the sample, things of that nature. Just be as clean as you can. Keep cleaning up all the time. I was told when I started that they expected to see, a pile of gloves at the end of the day when we're working in the lab in the waste receptacle, things of that nature. Personal protective equipment is very important, not so much in the idea for protection. It is for our protection to keep ourselves and our clothes clean, but the gloves, coats, etc., can really help to minimize contamination factors. I've actually seen videos and real-life situations where if you have a strong light source behind a person and they walk in from outside, if they shake a shirt or a sweater or something like that, you can actually see the lint and dust and stuff that can come off just off of clothes that are trapped in our clothes that we just don't notice on a routine basis. When we started into the lab, we actually started to put down sticky mats and all sorts of things like that, and it's just amazing how much we do carry around that generally goes unnoticed. We'll talk just a little bit about the labware, but everything needs to be as clean as possible. Sometimes when you're trying to do really low-level stuff, it's best not to have common labware. Sometimes it's best to have dedicated Mercury labware, especially when you're trying to do low-level 1631 down in the PPT, low PPT range. It's just, like I said, somebody else might be using some sort of glassware or Lemire or something for preparing something that might have significant mercury contamination. So it's best to have your own set of tubes, tips, volumetrics, all of those sorts of things for mercury of this level, trying to get down to this level. Every lab is probably set up a little bit differently, but most of the time laboratories will be somehow involved with, if not preparing the sampling equipment, whatever it is, to go get the water samples. Sometimes there's siphons or pumps or special scoops that take samples out of rivers or flowing streams of that nature. All of these things have to try to be as clean as possible. Sometimes the laboratories are responsible for the cleaning and upkeep for that, but once again, that's whole nother set of, that would be in the 1669 outlined in there as far as keeping everything clean. The lab does, and we won't go into it here because for the bottled water it wasn't pertinent or wasn't specifically related to what we were doing since we weren't sampling anything. So we won't go into equipment blanks and trip blanks and all those sorts of things, but there are numerous other blanks and things of 1631 nature listed in 1631 dealing with sampling. When you're doing samples, it's always best to try to at a laboratory to try to separate the lows and the highs, if you know that. And like I said, most of the time, lots of labs will know. I believe when they get routine samples in, they know which ones are the bad ones. A technician at an instrument, if they get that surprise bell ringer sample come through once or twice, you remember it next time, and you go up to the login and you ask, hey, please let me know when that sucker comes through again. So knowing your samples and where they're coming from can really help keep things clean and make the day go a lot better and keep from having a suspect or redigestions or losing time or not having confidence in our results. So if you do have samples that are higher than the top end of your curve, it's usually better to dilute them. So if you learn that XYZ company always sends in a sample and it's 2 or 3 times higher, dilute it 2 or 3 times down to get within the curve to give you good results and to minimize the carryover and the exposure of the equipment and the instrumentation so that it doesn't have a negative effect on the running of the samples of the rest of the run. Everything that touches, not even just directly or indirectly, but everything that touches the sample or the reagents or the gas or anything can be a contributor to contamination. So avoid all kinds of anything that you can do to avoid transference. If you think that your gloves get contaminated, you change them out right away. Anything that you can do to maintain air quality as far as the lid on, lid off, clean hands, dirty hands during sampling, all those sorts of things. Anything that you can think of to do to be clean is important to do. When you get the reagents in, and sourcing clean reagents ultimately can be important, as there is some background mercury in all the reagents. Getting the background down as low as possible is always important. So if you are unfamiliar with a new company, say that you can't get stannous from the same place that you generally do, and you don't have a feel for a particular new company or a history, so you have to get, we use Mallinckrodt. A couple of times we bought Fisher, and it's kind of bit us a little bit because we had more background in one or two of those. Fisher had a little bit more background than our traditional Mallinckrodt. You want to stay away from, hopefully that you don't have other things in the samples that are going to cause gold and silver. Like I said, will amalgamate gold. So it will bind it in there so that it doesn't react with the stannous chloride, and you won't see that. You'll have a negative bias, or you'll have a negative, you'll see a loss from what's truly there. Quenching in gold trap is much, much less of an issue, as all of those other things that get liberated during the reaction with the stannous chloride generally pass through the gold trap so that we get just mercury captured on the gold before we send that to the detector. If you do have, and the system that we use has a way for trying to dry out the sample stream, a little bit of water vapor does evolve off. In this case, with our GLS, I'm sure the same thing happens with the bubbling. There's a little bit of water vapor gets liberated as well. There is a PermaPure Nafion dryer in the system that we use, which I think is fairly generic, and what that does is that will pull out moisture from the system to avoid vapor getting into the fluorescent cell. If it does, it is basically just like getting a little bit of haze on a window. All the light doesn't come through in the directions that it should, and it will skew the detection, the light that actually hits the detector. We'll see a loss. This is the system that we use. It's the M8000. It does have an enclosure on the top. On the far left-hand side is where the air is filtered. Once the samples are prepared, the hydroxylamine has been added, the wait time has elapsed, they're loaded onto the instrument for calibration and analysis. The door is closed, you hit the go button, and the filter keeps the air clean above the samples and also evacuates any residual acid fumes that are evolved from the samples sitting there. That protects the equipment and protects the other samples next to it as well from getting any kind of cross-contamination. The GLS is a gas liquid separator. It does have some advantages as far as certain sample types, and I'm getting off the water focus here a little bit, but some sample types, the GLS does have some advantages. I've heard that fish samples, samples that have a little bit of protein maybe or a little bit of fats in them, tend to have a foaming effect, and the GLS virtually eliminates that being an issue, as it doesn't actually bubble. It flows over a really large post inside of the GLS, and that provides a very thin layer for the evaporation into the gas stream. The system that we use has a very good dynamic range, so we can extend the range if we need to up to 200, possibly 300. I've never gone and saw just how far I can go with it. As any instrument goes, the more you extend the range out, the more you make it harder to confidently see stuff in the very low end. So it's always best to try to, depending on your samples, to try to get into a working range where the majority of your samples are, and anything below or above that, you want to try to work those in either by a dilution or some other method of, or perhaps, if you know all your samples are only going up to 20 or 25 ppt, there's no reason necessarily to go all the way up to 100. You can reduce your top end, bracket your sample, or bracket what your samples are with your calibration is a good practice in general with any kind of laboratory equipment. We use Quick Trace software, which automates virtually everything. And with Gold Trap, there are a lot of valves and things going on. There's a lot of flows changing, directions of flows changing, volumes of flows changing. So the software automates virtually every step of that, so it can be completely unattended once you've got everything prepared and hit go. Before the experiment was done, because we were expecting that these waters would be very clean, we went through and tried to clean the lab till it was immaculate. We did add sticky mats. We replaced the HEPA, the filter on the system that provides air exchange to the room. We replaced the HEPA filter, which is the top picture there. That's the very large fritted filter that takes out particulates down to a very, very small size. Anything that could have been a source for contamination in the lab, the floors, the hoods, everything was cleaned extensively. The hood itself here, I was cleaning the hood, or excuse me, the enclosure, I was cleaning the hood to make sure that anything that we could do to be clean as possible was done. Also along those lines, we have some purging stations that we will bubble argon through in order to help evolve some trace mercury that's in the stannous, in the water, perhaps in the acid that we're using. You can purge almost all of the reagents. You can't purge the bromine monochloride itself. All of these reagents will have trace mercury, and anything we can do to reduce the background mercury in them will make it easier to get a good calibration and to have better results. It makes it a lot easier to get through all of the requirements of this particular method's calibrations. There's some extra stuff, basically, to be technical again. It's not a simple y equals mx plus b equation of the line. It's a CF factor, which we won't go into here, but a lot of people, if they're involved with, if they have experience with ICP, I guess that's something that's familiar to people with an ICP background. But there are several things as far as how close the blanks have to be to each other. There's a lot of details in getting a good calibration, and one of the major things that I've noticed over the last couple of years since I've done this project is the cleanliness of the reagents, and getting them cleaned up is very, very important. So we take the water that we use to create reagents with, and we take some 3%, and we purge that with argon to try to flush out or evolve out some of that background. We can do the same thing with our stannous, and we can even do that with a hydroxylamine, which sometimes does seem to have a bit more background contamination. We use clean water. It's already 18-something megaohm from a laboratory clean water system, and then once again, like I said, we purge it. The Gold Trap, this Gold Trap inline on the lower picture here is what is feeding what is transferring the gas over to the vessels. The gold is there to try to grab anything that is in the gas before it reaches the reagents. And we've got our wonderful sticky mats here also. Try to keep down tracking in particulate on our clothes and shoes. For this particular method, once again, like I said, we were going to be very, very low level, we thought. So we took extra care with loaded up the sample vessels that we were going to use, and I did just a ton of extra ones that we would need to use. We would the clear liquid in there is 10% nitric, and then I believe after that, it's been a few years, but then we also took added water, and we also did bromine, which is the lower picture, and then I also show that we inverted them to soak the caps and everything as well. And then, of course, we used our cleanest water. I used the purged water that was already ultra pure from our laboratory production system. Everything after we cleaned it was stored in Ziploc bags to keep any cross-contamination from happening that we could. So we tried to be as perfectly clean as possible. After we rinsed them all out, we cleaned them with DI, as I said. Then or our sample vials that we were going to use for the experiment, and also all of the bottles, once they were received in from all the various locations, the outsides of the bottles were rinsed off with some 3% HCl to help rinse off anything that might be on there from the handling of it. People when they were sending them in probably had handled them, who knows how they were handled in the production or everything like that. So they were cleaned with some HCl and some DI water, dried, logged in with a label, and then we stored them, I believe, in double Ziploc bags until we were ready to start digesting and do the project. Once we got them all cleaned up and stored, I took a spare enclosure on the lower left here, and we set up the argon purge to keep these things clean. This project was a couple of weeks long, and we did have several bottles. Each bottle, I think we had 2 or 3 of each particular bottle, and we wanted to minimize them just sitting around in the lab with some of the traffic that we had at that time. So we segregated them, and we even purged this particular enclosure with some argon before we stored them after we got done with everything. During the preparation, we used our pre-cleaned vials. We would measure out in this case, we were using 40 mils. That is something that can be adjusted if you know that you have higher or lower concentrations. You can use 20 mils. It all depends on what you're going to be delivering to the detector ultimately, where you want to try to range in, stay in with the working range of your calibration and your equipment and of that nature. In this particular test, we used a certain amount of acid and a certain amount of BRCL, and it digested for 12 hours just at room temperature. Room temperature is the general way that this test was set up. If you do have some of those wastewaters that I was alluding to, or I was going to mention before, sometimes they have an excessive amount of organic matter that's going to be binding or trapping the mercury, and sometimes it requires excess or more bromium monochloride than these cleaner waters would, and sometimes to get the digestion process to speed up, sometimes those samples will be put into an oven at 50 or 60 degrees C to increase the reaction of the breakdown of the organics to release the mercury. In our clean water tests here, after the 12 hours, we added 60 microliters of the hydroxylamine to get rid of the excess bromium monochloride. The method does have, and there's a myriad of other control checks, but these are the ones that we chose for, these are the control checks that we chose for this particular method or this particular project due to this being fairly assumed clean waters. So we did a quality control standard, which was, in this case, was, that can be, in my interpretation, that can be a second source for the primary mercury standard is what we did here. We had a source of mercury to create our calibration, and then we had a second source from another company that we also ran through the same dilution steps to get it down into the same range. And we basically are checking the two companies against each other to make sure that when they say it's 1,000 ppm, we verify that with two people saying that they're at that range. It's another check to make sure that things are right with the real world. The ongoing precision and recovery was something that in this case, with this particular method, is run at the beginning and end to show that the reaction of the chemistry and that the instrumentation is staying stable over the course of the entire run. So you run a check at the beginning and the end, and they have to be within a certain amount of closeness to what you tell the instrument that they have. Spikes, the mentality for spikes is that there is other things in most samples. Sometimes those other things, it's in a perfect world or in the world, it's not just the analyte that you're looking for and H2O. There's a lot of other things in there that can affect the chemistry being used in this particular case in this methodology. So what you do is several of the samples you will take and spike it with a known amount of mercury, and you know how much should be in there, and then that gives you a feel for, okay, is the XYZ constituents of the water sample, is that affecting my recovery and therefore affecting my actual read of what's actually in there naturally, in addition to the spike. So you'll do a spike and a spike duplicate for surety, I guess, to see how those other things in the water affects the chemistry being used in this case. Method blanks is just to make sure that you can read back that you're clean. It shows that you have clean technique. If your method blanks are showing up dirty, that means that you are not keeping equipment or reagents as clean as possible. And then you got to maintain records of when you brought your samples in, when you opened reagents, all those sorts of things. Those things can really help when you're trying to track down something that goes wrong in a project or on a day-to-day basis. Our procedure, after a couple of tries, I got a really good curve. I believe I was within the range of somewhere between 3.5 and 4.5 RSD on my CF factor, which is pretty good. They allow up to 15%. And then just on the left here, we have a graphical representation of what the curves look like as they come off of the instrumentation, their relative size. In this fluorescent mode, in gold trap mode, what happens is the area under the curve is quantified to give a response, and then that's what's used as in relationship to the concentrations that we've put on the instrument or told the instrument that this is, and then we can read back. Once we do our curve here, then we read back, and then the unknowns are determined from that calibration curve. Before you get started with all this, and these slides actually should be chronologically and during the project, we're done ahead of all of this. These are kind of the basic steps to get to prove everything is appropriate. This is basically showing, and these sorts of things when you do an IDL or an MDL study, it's basically looking at the instrumentation, can it get down that low? And it's also looking at, are you sourcing the chemicals? There's a lot of things that are instrument-centric. There's a lot of things in this particular method that are lab-centric or project-centric, depending on the cleanliness of the chemicals you get, the handling of the chemicals, and things of that nature, how careful you are with contamination control, how careful you are with calibration creation and that sorts of things. So this is, I always forget the number, CFR 136 Appendix B, 40 CFR, and it's basically just you run some low samples and you get your MDL, and if it's at the required level, then you can go ahead and start your project. Another thing that you also have to do, oops, we can kind of skip this one for now. I kind of went over this a little bit before. Matrix spikes, we spiked several of the samples to make sure that there wasn't anything in the samples that were affecting the chemistry, so we could have confidence in our results. Basically, like I said, a matrix spike is a certain amount added to it. The two lower boxes are basically just screenshots of where these things are set up in the software to do the math for us. But the method above here from the APA method states you need to be within 75 to 125% recovery. And then on the RPD is referencing how close your spike and your spike duplicate are. They have to be relatively close. And the results on the upper right here are what we actually got in the experiment. Okay, and then quality control sample once again was our second source, and I came back reading what I got on the left and had fairly good recoveries, considering that these were we're getting down to PPT range, diluted all the way from two different ppm primary standards, commercial standards. And then at the lower right, I basically did 3 runs once I got everything worked out and how to accomplish it. I basically did 3 runs, so I have 6 data points for the ongoing precision and recovery for one set of each for each of the 3 runs, and the percent recoveries there. Blanks, in this particular case, the method blank was the main one that we were concerned with, and as I mentioned before, it's a little bit difficult if you're not good and clean and source good reagents, clean reagents. If you have a lot of background, it will kind of skew the difference between your blanks. And that first non-zero point, which per the method is a point, is a 0.5 ppt. One of the concerns or one of the rules to do that is that you can differentiate your blanks from that very low standard to prove that you are clean and are doing the best you can to have good results. Also before, along with the MDL study, and I said that I should have really had these two things at the beginning to be more chronologically accurate. But the OPR, this is what you do before you start out your OPR. You get a little bit of data on how well your instrumentation and technique can produce good repeatable results, and that's an IPR study that you do. It's related to the OPR that you will eventually use to show that your system is maintaining calibration, it's maintaining its stability chemically and physically, that everything on the instrument is performing straight through. Nothing is changing and changing the results. We're not biasing or prejudicing our results. Here's just a screenshot of once the system was loaded up with samples in our software. It's really nice to be able to just look at it, look at the real world, look at the samples, and know that everything is loaded correctly, everything is in its proper position. Here's the results. All this talk and all the water was very, very clean. There was a little bit of a hit, significantly compared to the others, but nowhere near anything that would be of any concern. Australia had a little bit of something in it, and I do not know why that is. I did try to look up at some point back where this was coming from, or why this might be a little bit higher, and I wasn't able to find anything for sure. But Australia was the only one that was of any significance. So the water in general was all very, very safe. Here's a graphic representation of that, and it makes Australia look really bad, but if you look over on the left-hand side, really not very much there, much less than most water standards. That's the only one that was significant. So in conclusion, our 8000 Mercury analyzer is ideal for this kind of trace analysis. It does take a lot of care to be clean, to keep all that contamination out of there so that you don't get false positives, skew the results in that case, which over the years has been found to be one of the biggest reasons for disparity from accurate results. Like I said, mercury in all of these bottles showed no threat to human health. It was very, very low. That is basically that in a nutshell. I did go through that really quickly, so I'm sure there's probably going to be some questions. Anything that we can't answer, and I'm going to have to learn how to see these questions a little bit easier on the screen here. And I'll try to answer any of those, and then if we can answer them right here in this situation, we will feel free to email us, and we'll try to answer those when we can. Shelley, I don't see the questions. I can't see the questions.
I've assigned one question to you.
Okay.
Do you see it?
Yes.
Okay.
My screen is very, very
In the right-hand corner, there's by the X, there's a little box that will expand the big box. Can you see that?
No, I can't.
The question is, it seems that bottled water would be very clean to begin with. Can this ultra-clean, ultra-sensitive method be applied to wastewater which characteristically contains solids, etc.?
Yes, and that's what I was alluding to earlier. That's when you have to take other, like I said, this was a fairly easy, first project to do. All those other things and those other water samples, this is actually the prescribed method for a lot of those things. The concerns are all the stuff that gets in a municipal water sample can be interferences or causes, and there's also the concern about the digestion. Okay, I'm trying to read this in a tiny, tiny little thin thing there, but yes, this is used for that purpose. The concerns are mainly trying to alleviate any interferences that can be from all those other chemicals that are either inherent in there from the waste stream or from the processing plants, trying to clean up to get that cleaned up before it's released back into the environment. I hope that answered that one. Is there any other questions?
There is another one. Do you see that thing where you can break out the questions box?
Oh, okay, there we go. Yep.
Okay.
Thank you. Sorry about that.
That's all right.
Okay, the question is, we used a cleaning procedure to rinse the exterior of the bottles with hydrochloric acid. Is the water sample representative of the drinking water quality consumer after this cleaning procedure? I'm not really sure what this question is asking, but the reason for the cleaning was just so that anything that was on the bottles was not going to be a source of cross-contamination when we would be taking off the caps and handling them and things of that nature. What's inside the bottle was segregated from that, and we were trying to make sure that we didn't get anything into the sample tubes or anything handled differently. Okay, we'll get some more questions coming in. BRCL in 1631 and 245.7, the main difference, if I remember correctly, is the concentration that you use. And the cleanliness is completely where you source it from and how you handle it when you prepare it. We used some stuff from Environmental Express that is fairly handy. It's a 10 milliliter ampule, it's a Teflon ampule for cleanliness and separation, and it's added to 90 mils of ultra clean HCl, and that's what we use for the procedures. There are other methods that the old school method that's listed in the manual or in the method itself is actually taking the two dry reagents, muffle furnacing them to try to evolve off any mercury contamination and then making the solutions that way. But we kind of took the quick and easy method, as we didn't really have the facilities to cleanly, safely heat these chemicals to do the cleaning process part of it and then mix them up. Let's see, do you have any analysis one sample? We analyzed, I believe it was, and like I said, this was several years ago, but we did basically 3 runs of each, and like I said, some of the samples we had 2 or 3 bottles, so we were going to try to do a comparison of bottle to bottle, but we didn't have enough information to make that of really any interest. I think we did analysis, 3 times of each water sample. According to, I'm not familiar with all of the water standards. The next question is, the bottled water in the U.S. seems to be very, the bottled water in the U.S. seems very safe. All of the bottled water that we had, according to the rules that I'm aware of, there's either in drinking water, the standard in most places is something like on the order of 200 ppt, and like I said, some of that is different, and then I know that 12 ppt is something that's used for waters, lake waters, river waters, and things of that nature. So all of these are well below anything that would be considered safe to drink with the current thinking right now. What's the thought towards using a 0 in your calibration curve or not? No, we don't force through 0. We use the software that we use follows the methods, what is dictated in the method, and force through 0 is not part of that. Like I said, it's not a y equals mx plus b. It's not a regular linear curve. It's based on each point has a certain response, and the CF factor is calculated from the average of all those things, and that's what develops the final line. So it's quite a bit significantly different from a regular y equals mx plus b line, where you would have something like trying to force it through zero if the chemistry's not following it exactly that way, which can skew things. One sample. Trying to scroll down here. Recommendations for cleaning. We use Windex. We've tested it. The reason we use that is because almost everything that we use has some acid constituent in it. Acid's corrosive, so we are constantly trying to clean the work surfaces. Any spills on the instrument, any spills on the autosampler, any spills that happen inside the enclosure, we try to clean up. And we use the Windex because the small amount of ammonia helps to neutralize the acid while we're cleaning, and then we've also tested dilutions of the Windex and seen that it does not pose any, it doesn't contribute any mercury to our surroundings. So that's why we use that. Now with the instruments enclosure, there's some special plastic cleaning material that we use to make sure that we do not expose that to any kind of anything that's going to break down the plastic and cause it to age quicker than it should. All the reagents were prepared following the EPA 1631 method. The short answer, yes. The true answer, as I said, the method, there's new things out there. Like I said, Environmental Express gives a clean, handy, easy, snip, snip, shake it up, and you're ready to analyze ampule of bromium chloride that you just, or a bromium bromate that you just mix with some clean acid, and that's what we use. You can do it old school, like the method spells out, and taking the two reagents separately, the dry reagents, heating them with some sort of evacuation to get rid of any mercury that comes off of them, and then you make your solutions and mix it up as you go then. I've had one or two customers since I've done this that say that they do have good luck with that, but you have to have the facilities and the cleanliness to do those sorts of things. But I'm not endorsing what we use over anything else, and I've actually heard some good feedback from people that have actually been able to prep the solutions the old method and have been able to keep them clean and use them for several months without contamination issues.
Hey, John, I'm just going to go ahead. I'm getting a lot of this question. Everybody's asking if a copy of the slides will be made available. And yes, everybody will receive an email when a copy of the recording of this presentation and a copy of the slides are available for download. So
okay. And as I tried to say at the beginning, this is in no way anything comprehensive to 1631. This is just the bullet points that are most relevant to this particular project. 1631 is a fairly thick, it'll take a little while when you sit down to read it, and I would suggest if you're trying to get into something like this that you get very familiar with it first. There's some things that takes a little bit of time to kind of work out and exactly what to do, depending on the samples that you're doing, depending on your particular laboratory environment and things of that. It does take a fair amount of effort to get to this cleanliness level to assure that you're not going to give false high results due to contamination. Contamination is the biggest negative trying to do this since this mercury is so prevalent. Trying to read through here as I talk. Is there a difference in impact when we digest samples with microwave? I've never had the opportunity to try microwave digestion, so I really can't speak to that. In microwave digestion is generally more sample specific. I'm not sure, and I don't have any reference how those things, how that would be specific to this particular method. Microwave digestion is usually used, the little bit I know about it, on more like organic samples where you're trying to break down oils or lipids and things of that nature to release the analyte of interest. What's the reason for using the M8000 CF to instrument flow level? It's because of the gold trap method. The M8000, Fluorescence by itself is, there's CVAA, or CVAF, which is cold vapor atomic fluorescence, and then the other widely used, I believe, precursor was CVAA, which is cold vapor atomic absorption. CVAF gives a lot more bang for the buck. So mercury, you can see things. You can see lower because with fluorescence you just get more response than you do in AA, for one thing. And then also with the 8000, it's pre-concentrated onto the gold trap. So every time that we do a sample, it does take a little bit longer, but we get a stronger spike, which translates into being able to read lower, and being able to read lower with much more confidence than it can if we were just doing by CVAA, was the reasons. The instrumentation was basically developed for this kind of work. Recommendations for suppliers. We use O2SI and Environmental Express. We've used both of those, and that's where we get our bromine solution that we use to mix up our digestion solution. We like Mallinckrodt for the stannous and the acids. We get good clean acids. And the Mallinckrodt stannous, we've only had issues a couple of times here in the QC lab with getting something that was contaminated or wasn't, didn't seem pure, and we would have residual particulate or some that had been exposed to air. If it's yellow when you bring in your stannous chloride, then you know that it's already started to oxidize. If it's yellow when you prepare it, you don't have the full strength there that you need to do the chemistry. Other reagents, most of the stuff, like I said, we get either through Mallinckrodt for our acids and O2SI and Environmental Express. Environmental Express does have several nice kits for these things, and I had one customer that was using some really expensive acid that they used, and it was really good and clean, but I don't have a vast, expansive experience as far as what's the best. I know what we use, and we kind of offer that when we go into a lab. Some labs are already doing this, and some of these labs have actually taught me several things as far as their capabilities and what can do. So the best thing is to find a source that you believe is good and try it, and then if that doesn't work, you try something else. And like I said, there's a few things with purging that you can make some reagents that aren't maybe the best coming up out of the supplier, and you can clean them up to some extent to get down into the working range. But there's a lot of lab-centric stuff that has to be done too to keep everything clean. Okay, here's a really long question. Give me a second to try to read and digest it here. I'm really not sure how to summarize this one. So it says we use EPA 1631 for scientific purposes and research of water systems and aquatic life, but producers aren't interested in low levels of determination. I suppose I'm not exactly sure what his statement or question is asking for. I do know that the wastewater treatment plants, many of them use this method on their influent and effluent. I know that I'm not sure what the bottled water people do as far as testing for these things. I'm assuming that they have to meet certain criteria for that. I don't know if mercury is a hot button topic for them, or if they just test specifically for that. I'm sure at some point they do. Not sure how to answer or speak to that question or statement. What kind of messages comes to consumers of water? Produced water. I think the message is this kind is there's mercury in drinking water. Gosh, what kind of message comes to consumers of water? May producers of bottled water think that the message of this kind of work is there is mercury in drinking water? If anything, I mean, like I said, 12 and 200 ppt are some of the water recs for water quality, and this is way beyond it. If anything, this, I would assume if he's asking what are the water people producing the water, think about somebody like us doing a test like this. If anything, this is just saying that it's really good and clean would be my perception, but I can't really speak to the marketing or the bottled water people's concerns. Do you make your own BRCL and stannous chloride? Like we spoke to that a little bit earlier, we order from O2SI or Environmental Express for the bromine solution, and we mix that here right before we do the experiment. And then the stannous chloride is Mallinckrodt is our source for our stannous chloride. What comes to your attention in the area with the real problem with drinking water? I do not know. The subject of this project was just simply to do something that would be interesting and fairly, we weren't going to be dealing hopefully with huge problems of interferences or contaminants and things like that. We were fairly certain that we would be able to get some good results quickly as far as not having a lot of other things to worry about, whereas in a wastewater study you would have much more, you have to spend much more detail in looking out for interferences and chemical reactants that would interfere with the chemistry of the instrument. Let's see, when using Ziploc bags for storage, we have to trust, I asked that question way back, the same question is with, do you trust the gloves, or how do you trust even the chem wipes? In addition to cleaning the area every time I was putting something down on the end case that I would spill sample or a standard or reagent, I would have multiple paper towels down. Every time I would take a cap off and I needed to set it down during the handling or parsing out of reagents, I would put that down on the clean paper towel. So I was using all that. At some point you just have to try it and know what you can and can't do. So we use chem wipes for the large chem wipes for everything. Sometimes we'll use paper towels, but it's a matter of at some point experience that okay, well we think that we're getting something out of this particular lot or whatever of a certain thing. When handling samples, it seems that you use exhausting laminar flow cabinets. I can't remember exactly. I think we have got 2 different makers in the lab that we have now. I can get that information later. We actually have a little bit nicer system now than we did back when we started this, and we basically just had a hood for evacuating the fumes from the acids and stuff, which was basically pulling in the room air and letting that possibly contaminate the samples. Now we have, for some of our things where it's safe, we can actually, we have a laminar hood that produces clean air and gently pushes out into the lab, and that maintains a particulate-free area where we're having samples open, measuring samples, measuring reagents and things of that nature. But anything that is vaporized or off-gassing acid fumes, and the bromium monochloride is very bad stuff. It smells horrible. It's very bad for you. Do not breathe that. Do not do that in a laminar hood. I don't know who made ours. I'll have to get that information. I can't recall the names. I look at it every so often, and it just didn't stick in my head. So we use argon now with CVAA. Argon is important. You can use argon or nitrogen with the AAA models, but with argon, because of nitrogen and oxygen, some people even would use air for AA, regular compressed air, but the O2 and the N2s and stuff of that nature is what, if that's mixed in with the mercury sample stream going through a fluorescence detector, if the mercury does get excited by the light that hits it and then it releases some energy back, which is the energy that we're going to read, those other constituents, those other nitrogen or oxygen atoms in there will grab it before it gets to the detector. So that's the quenching that we're talking about. Energy is given off by the mercury, but it doesn't make it to the detector. It's not quantified because it's been cut off at the pass, so to speak. So that seems to be all the questions. So if there's any final questions, Shelley, or I think
If there are any questions that went unanswered and they're pressing for you, feel free to email John, and he will do his best to answer. But as I said, the presentation and the recording of this webinar will be on our website, and you'll receive an email to let you know when it's available for download.
Okay.
Well, thank you, everybody, for attending. All right. Good day.
Thank you, Shelley.
All right. Bye-bye.
Bye.